Yeah, hello everyone. Welcome to the third VISGAP session, and the session is called Application Retroperspectives. And yeah, we have 4 exciting talks. I want to mention first that please use the opportunity to post your questions.
Yeah, hello everyone. Welcome to the third VISGAP session.
For all the talks in YouTube and on Discord text channel. And yeah, so we start the session with a presentation from research topic to industrial practice and experience report, which is given by Petra Kospadnetic, Markus Rahut, and Hans Hagen. Please go ahead.
Hello everyone, and welcome to the talk from research topic to industrial practice. Today I would like to talk a bit more about the experience that many of us are probably familiar with, and I would like to highlight certain things, certain aspects of it, and see how can we actually bridge those problems. So, what does research collaboration actually looks like? Theory versus practice. In theory, the researchers are building breakthroughs, we openly communicate our findings to the industry, and then we transfer our knowledge to them, and together we make a better product. Together we lead towards we lead the industry on the path to product innovation. In practice, research results often get through undetected. The goals of the research community and the industry community are completely different. Development practices are also completely different and frequently very hard to combine. When it comes to the transfer of knowledge, it seems like the parties involved sometimes speak the same language but don't really understand each other. And then, above everything, something that we are all familiar with and have had to go through at certain point is the non-disclosure conundrums. So what may or may not be said, what may or may not be made public, and what are we actually allowed to publish. So we go through all the research, we do the work, we make it happen, and then it's very difficult to actually publish the results and the data to make that verifiable. So yes, there is definitely a gap between the research and the industry, and yet every day we are building bridges to cross that gap. But what seems to be the problem? Where is this gap coming from? I mean, the thing is that this problem is to blame on both parties, both research community as the industry community. We are all in this together. So from the research side, the problem is you have to make sure that your results are applicable, and they have to be applicable to different things. And so we actually seldomly do it like that. We usually focus on one thing. Then there are development practices. Research development practices are far from sustainable. Then it comes to the reproducibility and availability. Yes, we publish a paper, but how do you reproduce the paper? Is the data available? How are we enforcing those stuff? Transparency, frequently found when people are kind of cherry picking the results. Or, finally, publish or perish pressure, because we all know it, and we all know that we need to publish in order to get the work done and in order to get the grant money. But yes, those are our problems. And then coming from the problems from the industry. The industry is supposed to give us the possibility to know about the state of the art. And if we know about the state of the art, we should be able to use it, which is not always the case. Then there is a question of intellectual property. Who develops? Who owns it? Research allocation. They would like to put one man on a project which would approximately work for 10 people. Yes, sounds good. And then there is also the problem statement. Sure, they need solutions, but frequently it's really unclear what solutions are they looking for. So let's go from both sides. What are the requirements? What industry actually needs? What industry needs? Industry needs to have a possibility to have methods proposed that are tackling certain solution that they can evaluate. Further on, those methods need to be available so in order to implement, those methods need to be available to them. And then there are the legal concerns which serve the company to protect themselves from the competition. What research needs, we need a problem to work on. Okay, so we need a clear statement what is the problem, what needs to be tackled, what needs to be improved. And what we also need is possibility to evaluate what is available right now, and in order for us to find the sweet spot where to start from, or compare our findings to. Further on, we need the resources. Of course, everyone needs resources. And in the end, we want to disseminate our results, because the whole concept of research is supposed to be that we are researching something, disseminating our knowledge, so that someone after us doesn't have to repeat the same thing and start from zero. What are the challenges is actually meeting those two sides and requirements? Well, the problem statement. There is no highlight of areas which need to be improved. When you're researching something, you either have a contact to a person or you have no idea what's happening. So it's kind of on need-to-know basis that the communication goes towards scientists. Look, guys, we need this and this and this fixed. But that is at the point when the industry has already, one particular producer has defined one particular problem and they have reached out. There is no more global possibility to actually determine problems and for scientists to reach out when they think they might have a solution. What that causes is the problem that frequently scientists think that they are solving something, whereas the solution may not be needed as much as the scientists think so. Further on, there are roundtables that are tackling those problems. Sure, they are meeting research community and the industry representatives, but they tend to be high level. And frequently, things get lost as they propagate knowledge further to lower levels. And finally, data availability. So if there is a problem statement, there should be data available with it. But there is frequently no data available, and it's very hard to actually retrieve it. Then the research under confidentiality agreements. Restricted publishing. The research results are actually just not reproducible, because when you kind of slice off the things that you're not allowed to say and publish, what you have published is very, very hard to repeat. And you cannot really verify the methodology because it has been tailored for a specific data set that actually is not allowed to be published. So it kind of hangs in there, stays there for someone to become an inspiration, but you can never be completely sure that you have repeated the experiment and really it works. And then one of my personal problems that I really, really often come across, and it annoys me very much, are the software development practices. There have been studies before, and what they have reported is that you find scientists saying they're supposed to be reusing concepts, not the code, which is definitely not something you want to hear from someone who is handling code. Further on, they say there is no software to be delivered, so there is no need for best practices in terms of coding. And that is something that I like to call tumor-oriented programming. The code grows as new ideas come to mind, assumptions are hard-coded, and the code to be reused is copy and pasted. And once the project is done, no one touches the code because it's toxic. And what about the applicability versus reproducibility? So, as I said, just because we are computer scientists and we have the computer science training, it doesn't really mean we are good programmers. In Nature, they have run a study on 1,500 scientists and asked them if there is a reproducibility crisis. 52% of them said yes, and then another 38% of them, yes, a slight crisis. Wow, those are quite the numbers. And only 3% said there is no crisis. And this is not just on computer science. Prototyping. So the thing is, with computer sciences, we always depend on the prototype. But the question for us is prototyping proving a point or enabling further work? Because depending on the answer to that question, that is how we are supposed to be handling those prototypes. The specialized datasets actually lead to specialized solutions, and that is something that really frequently happens in our field. So you have a lot of solutions that are very, very specialized, might be similar, but yet you cannot transfer them. And also, because of that, you have unavailability of methods and or results, because you cannot really sum up all the specialized things at once. And just to top it off, add the human factor where everyone wants their results published. And let's be honest about it, typically it's not the bad results that get published. So what people tend to do is selective reporting. It's definitely a bad thing, definitely not something that should be made, but to be honest, we all know that has happened, and I would say that we all know at least one person that has done it. Not in the way this, sure, I'm just going to select this thing, but more in a way, yeah, let's just not mention that. It's not that big of a deal. The publish or perish problem, it actually says publish your work because you have to show that you're working on it. But when you're publishing your work, don't say too much about it. Don't say about the future problems. Don't say what needs to be tackled, because someone else might take your idea and then work on it further. So this knowledge transfer that is happening in the research community has the same problem for the industry. It's not getting anywhere. There is a lot of research also that is not oriented towards the industry, actually. They are doing research for research's sake, which is good and very much needed. But frequently it gets lost because no one actually knows how to apply it. What is it useful for? So that research should focus on communicating towards a wider audience. And when it comes to publishing, let's all be frank, industry and research collaborations, they have little to no interest in publishing. So for them, knowledge transfer is more like keep it in the house, teach us how to do it, consult us, whatever, no need to transfer that further. Those are quite a few problems, but I do think I may have at least certain solutions to fix that. Industry needs to make sure to state their problems, to communicate, recognize problems, and prepare data for those problems that scientists can work on, even if it's artificial data. So before the collaboration actually starts, there should be some artificial data so that at least some prototypes and tests can be made. The roundtable incentives, they should precisely define problems, and they should make sure those problems are reinforced with example datasets. The challenges recognize that those roundtables should be made widely available. We are all cooking with the same water. So what can be provided is the information about the current practices. Those information should provide insight into available methods and also communicate the industrial standards and their shortcomings. That way, when the research is conducted, we can be aware of the standards and what needs to be done. The applied research institutions actually here play a big role. They should be listening to the industry and at the same time know the research, know what is possible. Then they should be the ones providing connections where it's appropriate. And one thing that really should be encouraged is that the researchers at those institutions are officially required to conduct peer reviews, especially with emphasis on the areas of application, because when we are providing a peer review, we should be thinking about, okay, this is where this paper is applied, but here is a list of suggestions where it also might be applicable. Regarding the reproducibility of the research, there has already been a lot of good efforts out there, like ACM badging system, or papers with code website, or open science framework. Replication studies are needed. They provide the quality evaluation of the methods available and also should be able to identify and establish good practices. But finally, it is industry's task to actually do method applicability evaluation of work that has been done, what is useful and what not, and that should be available to the researchers. Once the research has been conducted, it needs to be made available, but not only in the form of paper. Not only in form of a talk on a conference. Research should provide examples, testing data, together with the expected results, so that it can be repeatable and verifiable. We should be providing simplified interpretations of our work, because not everyone reading our work is an expert, so we should give them hints and clues. What is this thing about? We should be able to suggest further applications, because just because it was applied on one thing, while we were researching, it is very likely that we have come across other ideas where this is also applicable, but we are not maybe very likely to follow them. So if we had this idea, why wouldn't we share it with someone? And also, what is very important and should be further reinforced through the peer review is the clear statement of method vulnerabilities. We all know that every method that we develop has the shortcomings. Those shortcomings should be clearly stated. In the paper, I have actually mentioned the null results quite a lot, because it has been a problem of the research community for a while, and there have been many different ways to tackling it. But forcing researchers to actually publish it in a scientific form is not a good approach, because we all know that research is just one part of writing a paper, and the second thing is actually doing thorough work to make it into a scientific form. This time is frequently not available to the researchers. Because of that, there should be informal experience report, which would provide the community with insight into what worked and, more importantly, what didn't. Those should be in non-scientific formats, such as blogs, such as conference talks, discussions, panels. We need to discuss problems, assumptions, and ideas, and give people ideas to work on further. Throughout the process of our research and code development, really the clean code should not be just a buzzword. Our prototypes should be coded with an intent to enable further usage, regardless if we do or do not think they will be further used after our work is done. There should be documentation ensuring repeatability, and by documentation, I don't think just putting comments in the code. I mean making sure that the environment is stated, dependencies, run scripts, everything. There should also be a feature summary separate from the code. So when someone takes over the code base, they can start from somewhere and they can figure out what can be done with this code base. Research collaborations with industry should make sure to have topic-dependent groups of research software engineers who know the problems and can help scientists provide better code. Also, all of the computer science conferences should give space to research software engineering so that we can actually establish best practices which are topic dependent. Visualization, computer vision, robotics, they all have a certain set of standards that should be taken into account when developing. And that is where the research software engineers come to. They're the ones who should be aware of those standards and provide a way for researchers to easier integrate new methods, new code, and new assumptions. There is no silver bullet for this problem, but the reproducibility just may be the thing that we need to really take care of next. When you're working on your research, make it available. Make the code available. If you're not able to make the code available, try to create minimal working examples. Data is crucial. We are all today dealing with data. In visualization, there is nothing to visualize if there is no data to visualize. Provide data samples. Provide ground truth. Give people a possibility to work further. Because only that way you will create a knowledge base that industry can look into and researchers can build upon. Thank you.
Thanks, Petra, for this talk. I think there are many relations.
Hello, everyone. My name is Renata Raidu, and today
research domains. So what I forgot to mention is that we have at the end of the session a question and answer session where all speakers are involved. So save your questions for the chats in YouTube and Discord. Or maybe later in the Zoom, you might be invited to join. The next presentation is entitled Lessons Learned from Developing Visual Analytics Applications for Adaptive Prostate Cancer Radiotherapy. And the paper is written by Renata Georgia Raidu, Katarina Furmanova, Nicolas Grossman, Oscar Casares Magas, Vitaly Moisenko, John Eink, Eduard Kröller, and Ludwig Muren. And the talk is presented by Renata. Go ahead.
Hello, everyone. My name is Renata Raidu, and today I would like to present you, on behalf of all my co-authors, our work on lessons learned from developing visual analytics applications for adaptive prostate cancer radiotherapy. Radiotherapy is one of the most common methods of treatment for prostate cancer. The aim of this treatment is to deliver a high dose of radiation to the tumor while sparing the surrounding normal tissues. Prior to the administration of the radiotherapy dose, an optimized treatment plan like this is performed. And this plan takes into account the locations of the tumor within the prostate and also the healthy surrounding organs, in this case the bladder and the rectum. Despite thorough planning, bladder toxicity, meaning acute side effects to the bladder or the rectum, remain a very common problem. The reason for that is that the dose is not administered all at once, but usually in a fractionated manner, with treatment protocols across several weeks, and during this period, the bladder and the rectum anatomy changes. This change, which you can see here in this example of day-to-day variations of the three main pelvic organs for a prostate cancer patient, may be due to natural anatomical variations, day-to-day variations due to urinary or rectal feeling, involuntary motion, motion of the patient, and so on and so forth. Recent clinical research suggests that anatomical variability can lead to increased radiation doses being delivered to healthy organs such as the bladder and the rectum. The necessity for a more drastic adjustment of the plan has been highlighted by several recent clinical works, and to this end, retrospective cohort studies are conducted to give information about potential subgroups of the population that face advanced risks of toxicity. The current state of the art, both in the clinical and in the visualization domain for radiotherapy, are the following. In the clinical domain, previous studies have not been able to relate organ variability and potential toxicity, mainly due to a lack of exploratory means. And most of the retrospective cohort studies have been inconclusive with regard to the relation between toxicity and organ variability. From a visualization point of view, many visualization methods have resulted in a large collection of prototypes, visual designs, techniques for radiotherapy without ever being adopted in clinical practice, which is something that we documented also in last year's state-of-the-art report on visual computing for radiotherapy. What we encountered in that literature search was also that two-dimensional representations are well encountered in clinical practice, but this does not even go to three-dimensional representations, while visual analytics is still at its infancy. So the goal of our joint work was to develop an application for improving prostate radiotherapy, and this application should be actually used in clinical practice. In the presented work today, we want to show you a successful example of bridging the gap between visualization and radiotherapy, and I would like to give you our personal opinion about the lessons learned during the long co-design process of this application together with the domain experts. In general, in our work, we followed the following pattern for our design process. Initially, the visualization counterpart of this project tried to learn more about the domain of application, mainly the workflow and available data. In clinical practice, the evaluation of a treatment plan is currently done in two ways, either with anatomical 2D views, such as this one in the left-hand side, that depict how the dose affects the tumor and its surrounding organs for a given point during the treatment period, or with those volume histograms, DVH on the right-hand side, which are plots that represent the amount of radiation which is administered to the volume of a specific organ. These two approaches suffer both from several issues. The anatomical views, on one hand, they do not scale well for the exploration of many patients and many treatment points at the same time, while the dose volume histograms do not provide a link to patient anatomy. In practice, they show how much of an organ might have been affected by harmful radiation, but they do not show which specific part was harmed. In this work, we had data from 29 patients available from our two clinical collaborating institutions, and this dataset includes an initial 3D dose plan designed prior to treatment and 12 subsequent sessions for each patient, so in total 13 fractions for each patient. For each of these stations, we were provided with pelvic organ segmentations in the form of contour lines, obtained by manual delineations which were done by the same radiologist, and for all patients, we had prostate, bladder, and rectum delineations, and also retrospective information about toxicity manifestation for each patient. The next step in our process was to define the problem. The main goal of the clinical researchers was to demonstrate the significance of dose plan adaptation to changes in the anatomy of the patient throughout the course of the treatment. And this could be done by documenting the effect of the organ variability to the dose distribution. We performed a long and extensive task analysis with 4 clinical researchers from the 2 clinical counterparts of this project. And we started small, looking at only one organ, the bladder, to begin with. And here we cared about, for example, how much does the organ shape vary through treatment time, how much does the administered dose vary through treatment time, how much does the administered dose deviate from the initial plan, is there some toxicity risk? And then we went bigger, moving to multi-organ cases. And here we cared about the same stuff, but moving on to a multi-organ focus. Then came the phase of brainstorming and prototyping, the results of which you can find with detail in our previous papers on their respective applications, and here I'm just going quickly through them for the sake of time. So the first application with a single organ focus was Bladder Runner. And the contribution of this work was the design and implementation of this tool, which allows clinical researchers to visually explore and analyze the impact of bladder shape variations on the dose distribution during the course of radiotherapy treatment. The investigation of the radiation-induced bladder toxicity in Bladder Runner could be conducted both for individual patients or in a cohort manner. To assess the value of the Bladder Runner, an initial informal evaluation was performed with 3 medical physicists from 2 clinical institutions, and the evaluation participants commented that the tool can potentially widen their knowledge about patients that are more prone to develop toxicity, allowing them also to analyze their cohorts more efficiently and less time-consuming manner. Bladder Runner had now to prove also its clinical value. Using the Bladder Runner, Casares evaluated whether parameterized bladder-shape descriptors can distinguish between patients exhibiting and patients not exhibiting toxicity. Here they performed a matched case control study on 258 patients using the Bladder Runner, and the result of this study showed that higher toxicity risk correlates with specific bladder shapes. For the first time, a clinical study was able to confirm with the use of our tool that bladder shapes can be used for toxicity prediction. Now it was time to go bigger. That's the point where we went back to the brainstorming and prototyping phase to extend the previous work to a multi-organ approach. And this resulted into the Pelvic Runner, where the focus was to determine how different pelvic organs vary through treatment for different patients, and whether, for example, there are the so-called main modes of variation, meaning groups of patients with similar day-to-day anatomical variability. 4 usage scenarios were conducted by 2 medical physicists for the evaluation of the Pelvic Runner, and the domain experts commented that the tool offers them a way of identifying uncertainties within the treatment, and could also give indications of patients that will fail or may develop toxicity from the beginning of the treatment, allowing them in this way to adapt their employed strategy. Within the clinical setting now, Furmanova recently analyzed the organ shape variabilities with respect to the mean shape as computed from a first given number of treatment points using the Pelvic Runner. This study concluded that in most patients, most of the organ motion can be captured and predicted within the first 4 time points of treatment, and using multiple pre-treatment scans captured over the first 4 consecutive days are enough to identify and predict patients with higher organ shape variability. So now it was time to go bigger again, and for this reason, we had to go back to our brainstorming prototyping phase, out of which vapor was created. The Pelvic Runner did not include functionality for assessing the impact of organ variability, dose distribution, and toxicity risk, and the domain experts thought that this could be a promising and useful decision-making tool for radiation oncologists. So at this point, we added this functionality. So this work is under submission right now, and the thorough evaluation and clinical assessment is actually ongoing. And before I go to the dissemination step, I would like to take a look at the lessons learned so far. So within the first part of learning the domain, this collaboration had already started with other projects many years before the Bladder Runner. So a main point is to build a long-lasting collaboration. Second, by the time we started working on the Bladder Runner project, the visualization researcher of this project already had a good understanding of the field of radiotherapy, and the domain experts had a very good overview of the limitless possibilities that visualization offered. This work started small, with a focus on a single organ, and extended to multi-organ applications little by little, with more and more sophisticated additions. Also, for the visualization, researchers that were involved in the project, obtaining a very thorough knowledge of the data and of the existing workflow was really fundamental. In our case, a lot of reading has been done, but the most significant part was actually spending significant time within the environment of the domain experts to observe the workflows, And also what we did was that we tried to target contributions and publications in both communities. In the definition part, for our application, it has been crucial to conduct thorough tasks and requirement analysis together with the collaborating domain experts. And this actually has been the most time-consuming step of the process in all three applications. The tasks might be refined during the iterative process of developing increasingly sophisticated applications, but in our opinion, it should be triggered always by the experts so that it can include all must-have features in the final product. Now, within the brainstorming phase, we found out that although exploring and experimenting with different kinds of solutions is an enjoyable and creative process, developing applications that have higher chances of being adopted in clinical practice requires actually more rigorous and systematic approaches. The inclusion also of at least one domain expert in the design phase is crucial for success, and in general, having such open processes require building a high level of trust among partners. For example, to be able to have a dialogue from our side, would this be useful and desired in our application? And from the side of the domain experts, for example, which strategy could be actually used to do that? In general, not all investigated strategies made it to the final applications, and some parts were actually simplified. So the dose variability is a very good example of a simplification. In the bladder runner, it included very sophisticated unfolding steps and so on and so forth, which actually would be unfeasible to adapt. And in the final product, they are much, much simpler. In the prototyping phase, we realized that creating and maintaining reusable visualizations might be really tough. And although a more efficient use of resources would be required, it's not really easy to determine how. Prototyping, for this reason, was used as a means of showcasing, and ideally, the software should be made open source. In our case, this was not possible. Also, in some cases, it might be useful to consider changing environment. This has happened, for example, the bladder runner was done in one environment, then for the pelvis runner, in order to ensure scalability and extensibility, we actually had to change environment completely. Evaluation is not always an easy task. In general, we relied on common best practices. However, what we found that was particularly interesting and insightful was to evaluate additionally our work through an assessment within the domain expert settings. So both bladder runner and pelvis runner were used in clinical studies, and this was very intensive, very detailed crash test, let's say, to determine which features of our tools are actually helpful. And these provided us with very valuable insight for following extensions. In this project, we did not look into certification options, as the retrospective clinical studies could be performed with the existing prototypes, but in general, clinical applications are required to undergo strong certification processes. A very interesting aspect of this project, which links also to the certification processes, was to have strong support from an industrial partner that actually has an interest in the developed applications and or is willing to fund the research and or is willing to integrate the developed solutions into a robust framework. Finally, for the dissemination, in our case, dissemination has been necessary to be able to convey the context of our work at all stages of development, first of all to our collaborators, so that they can understand what we're doing, we can process with brainstorming and also try to improve our applications, but also for them to be able to conduct further studies with our applications. And second, with respect to dissemination to the general clinical research community. Also, we saw dissemination as an initial step, as I said, for brainstorming and as a way of generating new ideas for future directions, also with other people except for those involved in this project. So with this, I would like to conclude my talk and say that although the presented applications have very specific goals and objectives, we hope that the findings and knowledge obtained during our co-design process could be applicable also to other domains. And one main take-home message is that building applications which are here to stay actually requires a very long iterative design process, which in our case is still not over. So with this, I would like to conclude my talk. Thank you very much for your attention, and I would like to thank also our funding providers.
Thanks, Renata, for this very interesting talk. I personally liked the process overview because it's like really representative for many visualization projects in cooperation with domain experts. Keep on posting your questions on YouTube and Discord, and we head to the next talk, which is entitled How the Deprecation of Java Applets Affected Online Visualization Frameworks, a Case Study by Martin Skrotsky. Please go ahead.
Welcome to my talk in this year's VISGAP workshop. The title of my talk is How the Deprecation of Java Applets Affects Online Visualization Frameworks, a Case Study. My name is Martin Skrotsky, and I'm currently a postdoctoral research scholar in the ITHEMS workgroup at the RIKEN Research Institute in Wako, Saitama, Japan. First, for some historic motivation. We are placed in the late 1990s in Berlin, Germany. The internet is ever growing, and more researchers discover this new technology as a means for their work. So, also a group in Berlin who's on the lookout for an online visualization framework for mathematical content. This framework should satisfy 3 major goals. First, it should be interactive. The users should be able to discover the mathematical content by playing with it themselves. Second, it should be accessible. That is, no specific software or hardware environment should be necessary to be able to run the framework. Third, it should serve as a communication platform not only for recreational mathematics but also for research work. When creating a software framework, a first obvious choice to be made is that of the underlying programming language. Going back in time, there were several popular languages. For instance, Fortran, C, or C++. However, all 3 of them have a common shortcoming. That is, they are machine dependent. They require compilation on the user's device. While there were already several workgroups working on mathematical software, no easy exchange of the software was possible because of this machine dependency. In 1995, a new language came to the market that promised to alleviate this shortcoming, namely the Java language. It comes with its own runtime environment that is installed on the user's machine. The runtime environment translates bytecode into specific machine code, so the programmer can focus on writing the bytecode and doesn't have to bother with the specific machine. It is also installed with most contemporary browsers, so that when looking at a possible user base, the users that are able to execute Java programs are basically equivalent to those users that use the internet. In terms of easy and lightweight interaction software for online applications, core functionality is included in the JRE, so that when downloading a software, this core functionality is already present on the user's computer and does not have to be transferred, causing for lightweight programs. Java also comes with a great GUI support, which sets it aside from the other 3 popular languages of the time. Therefore, it is very much accessible and very suited to create easy, interactive online applications. These reasons were considered, and the Java View visualization software was born towards the end of the 1990s. The Java programming language came with another strong feature for online visualization, namely applets, an opportunity to easily export your whole program into a web page. But what is their current status? Well, for a long time, when you tried to execute an applet, you saw a warning somewhat like this. Shortly afterwards, when trying to execute an applet, you wouldn't just see anything. So what happened? Well, these Java applets, on the one hand side, they had a strong competitor in the form of JavaScript, which was widely supported by many browser vendors and is extremely lightweight and easy to handle. Also, the JRE environment needed frequent updates, which was a hassle to many users, but not updating the environment caused severe security problems. So these reasons caused that the applet technology was deprecated in Java version 9 and eventually removed from Java version 11. That left the Java View visualization framework without one of its core functionalities, the easy web export. So how did the framework recover from this? What developmental changes were made? This will be investigated in the following. Let's now consider some general challenges to software frameworks, which we will consider in the light of our case study of Java View. First, how to react when a main use case of an application is put to the test. In the case of Java View, the deprecation of Java applets made the software framework lose one of its core functionalities, the easy export to web applications. Basically, there was one major question to be answered here. Is this really the one use case that the software has, or are there other possibilities, other use cases it can follow? If it was the one use case, obviously it would be necessary to consider different competitors in the field. We can't go into this in this talk, but I'd like to refer you to the paper to see a discussion of other web framework competitors like 3JS, Cindy.js, or the VTK.js framework. If it is decided that there are other possibilities for a framework to continue, it is necessary for the developers to definitely follow those and spend all their time and effort on these other possibilities and not waste on a use case that is no longer valid. And that is exactly what happened to Java View. The development team decided to toss the web application export at some point and rather follow the development of Java View as a standalone application. Of course, now that causes for other competitors in the field. In this case, it would be MeshLab or the Seagull framework, for instance. However, Java View still found its niche as a Java visualization toolkit, while there were no other toolkits that are still maintained available within the Java language framework. As a second question, what aspects of software can be maintained by container technology? Well, in the field of computer graphics and visualization, it is customary to have experiment accompany a paper or an article. These experiments can easily be provided with a container so that future generations can recreate the experimental setups and provide their own improved algorithms and compare them with the standard literature. However, when looking at a whole and complete software framework, it is not really feasible to provide a container. Consider the example of Java View. If there was a container available that would contain an older web browser that still supports all the applet technology, the easiness of the original approach would easily be lost. Because while you can still run it in the container, you can't integrate any of this technology easily into an actual web page. So the easy interaction and approach to the software cannot be maintained via a container. Third, how does the choice of the programming language affect a software framework? We've seen in this talk that Java was an obvious choice for the Java View framework to be written in. However, this same obvious choice caused this big problem when it deprecated Java applets. How to treat this challenge? Well, one choice is to simply stick with the language and focus on different aspects, like JavaView did, running a standalone version without the easy web export now. Other frameworks went different ways. Consider the Cinderella visualization software, for instance. Nowadays, it has a Cindy.js, a JavaScript version available that is fully compatible with the old version. Thus, the developers spent a considerable time and effort of providing an up-to-date software package that is still compatible to the old one. This comes, however, with the translation of the main core functionality into a new language, which has to be stamped by a development team. Fourth, let us consider what other basic building blocks of a software framework are subject to change. This is not only the programming language, but also, for instance, the underlying hardware. Users of the software framework have more and more potent hardware available, which they want to use with the software. There's no use to them if they have 8 or 16 cores available and the software only runs on a single one of them. So a software framework has to adapt to the ever-changing hardware environment. This is not only the performance-wise part, but also the output devices. Consider the recent rise in display resolution, where 4K and 8K displays are available to the users. The software framework, and a visualization framework in particular, should make able use of these capabilities. Finally, also new input devices are available from the realm of virtual reality that lets the user handle the geometries more intuitively. Using and enabling the usage of these devices in the software framework is utterly important to provide a modern framework concept. As a fifth aspect, let's consider open versus closed source software framework policies. On the one hand side, if you have an open software framework, you can count on many developers easily accessing and contributing to it. However, all these contributions, in terms of pull requests or emails or feature requests, need to be handled by a team, a core developer team, which cannot focus on their own development projects in this administrative time. So if you have a smaller development team, it might not be worthwhile going open source, but rather staying closed source and focus all your time and effort on the development of your software product. That is the way the JavaView software went. Finally, let us consider the case of competitors coming into the field. The area of online visualization toolkits is now taken up by 3JS, Cindy.js, VTK.js, or other partners, like processing language or Python Jupyter notebooks. The JavaView software framework moved away from this field by going into a standalone version. This was a conscious development decision. However, even in the standalone version business, now there are competitors like the VISGAP framework or the Meshlab software package. Which leads us to our final question. Should all software be saved? The JavaView software framework, discussed here as a case study, shows that a software can be saved if the necessary changes and developmental decisions are made. However, whether a software should be changed is rather a question as to whether these changes can be made. A gap in visualization can easily arise in any software in a situation where the outside factors are changing. We can only try to learn from the presented examples and the historical developments and the decisions that have been made in order to try and bridge gaps we are facing. We might, however, come to a conclusion that knowing effort it takes to adjust a software system is not worth preserving it, and it is more beneficial to move on to other approaches. The silver lining on the horizon here could be that there are always other approaches to turn to. And with that, I would like to thank you for your very kind attention to my talk.
Thanks for the talk, Martin. I guess some of us faced the issues of the disappearing applets. I remember, for instance, Wordle was one of the tools that was accessible online via applet and suddenly disappeared with Java 11. Okay, so the last talk will be given by Ulrich Günther and Kyle Harrington and is entitled Tales from the Trenches, Developing SciView, a new 3D viewer for ImageJ community. Go ahead.
Welcome to the talk accompanying the paper Tales from the Trenches, Developing SciView, a new 3D viewer for the Fijian ImageJ community. I am Ulrich, and I come from the Center for Advanced Systems Understanding in Görlitz, Germany, and I am also associated with the Center for Systems Biology Dresden and the Max Planck Institute of Molecular Cell Biology and Genetics in Dresden, Germany. This is work done with my collaborator Kyle Harrington, who comes from the University of Idaho. So, let's first talk about what this Fiji thing actually is. So, in talking about Fiji, I am unfortunately not talking about this one here, but I am talking about the very popular image processing software Fiji. Since Fiji was published in 2012, it has now been cited almost 20,000 times. And Fiji is actually a backronym for Fiji is just ImageJ. And the distinction between Fiji and ImageJ you can imagine just as between the Linux kernel and a distribution. Fiji is a distribution of ImageJ including a lot of plugins. Fiji is written in Java, that's what the J in ImageJ is for. It runs on Windows, macOS and Linux via the Java virtual machine. And Fiji provides a GUI and headless operation as well, for example for running batch operations on clusters. And it provides composable image processing building blocks named ImageJOps that both developers and users can harness. 3D viewers in Fiji have a long history, going back to the original 3D viewer introduced by Benjamin Schmid in 2010. And another one was developed around 2015 named Clear Volume. With this development I was also involved, and Clear Volume came out of a development of a viewer for high-speed volumetric microscopes where you could show the data as it was acquired on the microscope, which is shown in this little video here. This is a running acquisition of a developing embryo of a C. elegans roundworm acquired with a high-speed volumetric light sheet microscope. However, the capabilities we had back then were not enough for what we actually wanted to do. So we decided to develop a new software package that enables development of visualizations on the desktop, but enables you also to transfer these developments quickly to virtual reality headsets and also to distributed systems such as caves or power walls. The software that came out of these developments is named Scenery, and here I show a demo video of a recent project we did with it named Bionic Tracking, where we track biological cells via eye tracking in virtual reality. And this kind of showcases some of the features of Scenery, namely volumetric rendering, out-of-core rendering, mesh rendering, virtual reality support, and support for external hardware such as eye trackers. And behind the scenes, or Scenery, pardon the pun, is actually Kotlin. Kotlin is one of the fastest growing new languages for the Java virtual machine at the moment. The backbone is a scene tree based renderer. Scene trees were introduced by Tavanrad Kubish at GPU TechConf in 2014. and we provide in Scenery a flexible renderer architecture with both Vulkan and OpenGL backends, and the render path used is switchable on the fly and can be defined with simple YAML files. Scenery also provides a unified interface for VRPN input devices, such as gloves or joysticks, and provides also support for head-mounted VR goggles via OpenVR. In addition, it's also network aware. You can use it to connect multiple Scenery instances together for clustering use over the networks and, for example, construct a cave system with it. Now to go a little bit more into the distinction between the two software packages. So Scenery is intended as a backend library. It doesn't provide you any user interface apart from what it renders. And SciView is the ImageJ and Fiji front end. Involved with the project are these awesome people. Kyle, I already introduced, Tobias Peach, who is responsible for the out-of-core volume rendering based on his Big Data Viewer software, and Curtis Rudin, who is, well, essentially Mr. ImageJ. To go a little bit more into the division between the two packages, SciView is responsible for all the image processing and mesh processing done and provides polyglot scripting. So you don't need to actually dive into Java or Kotlin if you want to use or extend SciView, but you can use a REPL or scripting environment to control or augment it with Python or Ruby or Clojure or all the scripting languages supported by the SciJava scripting environment. Scenery and SciView share a user and developer friendly API, and Scenery brings into the mix the support for desktop and VR/AR headsets on and distributed machines. And of course the out-of-core volume rendering I was already talking about, and the cross-platform capability to run on Windows, macOS and Linux. Now in this slide I want to go into a little bit more detail about our development and delivery process. We make heavy use of the features GitHub provides. So for example, each new feature or bug fix that is implemented starts out as a pull request, and only if after this is merged into master it actually ends up in a SciView release. And with every commit that is made, either in a pull request or on master, we trigger a continuous integration build that is run on Windows, macOS and Linux via Travis CI, AppVeyor or GitLab. Now you might ask, why are you actually running that if you are using Java, which generates cross-platform bytecode? Well, the same code is actually run on all the platforms, but in the implementation of the Java virtual machine, there might be slight differences, which is why we are testing on all the platforms. And the most recent addition to this testing environment is actually GitLab. And GitLab we use in Scenery for creating graphical tests, where we compare a known good set of screenshots to screenshots generated from the current commit, and then generate a visual diff via the Argos CI software. And if all of this continuous integration process runs smoothly, the build completes successfully, then we upload the result to the SciView update site, either to the release update site if it's an actual release that was tagged on Git, and if it's not a release, it gets uploaded to the unstable update site, where essentially all new developments end up, such that we can quickly iterate also with users. Now a word more about the update sites. Update sites are Fiji's way of getting the developer's software as a plugin into Fiji, and it works by simply enabling any given update site in the updater. This list is also generated from a GitHub repository, but you can also add your own update site manually, which can be hosted on your own website or on the central sites.imagej.net page. Now let me actually show you what SciView looks like. This is a video of the SciView main window. Here we show the Game of Life 3D demo, and you can see the main rendering viewport and below it the main ImageJ viewer window, and of course also the scene list and the inspector view, as well as the control window of the Game of Life. We have used SciView already for a set of use cases. For example, here we used it to visualize the development of zebrafish vasculature, the blood vessels of the zebrafish, over a duration of 68 hours. And this is actually a segmentation rendered as a volume because we wanted to highlight all the different parts separately, which you can see by the color code here. This is done using an earlier version without out-of-core volume rendering, so this visualization was actually scripted. Furthermore, we have used SciView for generating visualizations of single-cell segmentations of proliferating stem cells in regenerating mouse incisor tooth. These are the yellow dots there. And also for simulation of neurodevelopment along a morphogen gradient, which is shown in the middle of the video, with neurons growing connections between the sensors in blue and actuators in white. Vladimir Ullmann has used SciView to develop a software named SimViewer, which is used for developing algorithms for automated analysis of microscopy images, for generating ground truth for these algorithms, because in microscopy you in principle never have an actual ground truth. So we use these kinds of software to generate plausible looking images from simulated embryos. And the SimViewer software then is used to visualize what is happening with the cells, what are the forces acting on each cell, which is shown here as arrows. And the actual software driving the simulation is EmbryoGen, which is written in C++ and it communicates with SciView running in a JVM over 0MQ. Now to summarize, we have developed a modern visualization tool for the Fijian ImageJ community. It can use Vulkan virtual reality, out-of-core volume rendering, and all the other features provided by Scenery. And of course the mesh and image processing utilities provided by ImageJ in Fiji. The software is polyglot by design, which we think is also very good in terms of longer-term sustainability. You can bring your Python, Ruby code, whatever, we take it. You can use it for scripting the software, for generating user interfaces, for augmenting it. And we're also happy to see that SciView is now getting picked up as basis for new developments. For example, for the artificially generated microscopy images I was showing in the slides before, or for a new neuron tracing app named SNT, which is going to be the successor to Fiji's simple Neurite Tracer plugin. Well, the future. So in terms of long-term sustainability, we hope to have provided a solid basis, both from engineering and a community point of view. Funding, of course, is always a bit of an issue, and research software is only slowly getting acknowledged as being useful by the funding agencies, so we hope that this is a longer-lasting change that will also be extended. And we hope for less VISGAP and engaging more with the visualization community, which is why we're here. We are already well engaged with the image processing community, but we would like to be more in exchange with the visualization community for better visualization algorithms, more exchange in general, because we think we have still quite a bit of room to improve in terms of visualization and rendering algorithms. We would like to thank a few people here. I want to highlight here Tobias Peach, who contributed the out-of-core volume rendering, and Curtis Rüden, who is Mr. ImageJ and an extremely helpful person in general for all development purposes. Also big thanks for Stefan Gumhold from the Computer Graphics and Visualization Group of the TU Dresden for help and support. And all the software I have talked about is available as open source. And SciView can be found on the GitHub repository as well as a Fiji update site. And our community can be found in the GitHub channel shown, as well as for all kinds of questions in the Image Sciences forum with the SciView tag. And with that, I conclude this talk, and I would like to thank you for attending this, and I look very much forward to the discussion following the talks. Thank you very much.
Yeah, thanks for the final talk. And we come together to the question and answer session. You find on Discord the Zoom link, so that you can just come by, as Thomas Wischkol, for instance, did. So yeah, there are already a couple of questions in the chat, so I will probably just go paper by paper, offer by offer. So I will start to ask a question to Petra. Just one question from my own. I thought like patents, you mentioned it in the paper that patents are some way of publication in industry. So I am not in this. So can you please tell me if a patent for itself could be also valuable for a researcher? Some part of a PhD thesis, for instance.
So what I know that has happened to some of my research colleagues is that they were working on something, and what they have developed seemed quite good. So their research group decided to do a patent with the industry, and all of a sudden they were no longer allowed to publish on it. Whether a patent can be used as a research contribution, I'm not really sure, because they are rather specific, and the reason why patents are created. So I'm not an expert here. This is just my somehow insight on it. The patents are here for legal issues, so that someone can compare whether there is some legal reason, legal credit, whether something can be considered a copyright issue, for example. But I don't think really it gives benefit to researchers. And I would really like to hear on that topic more.
Okay. So there are a couple of questions for you. So Christina asks, do you have a suggestion on how to create a knowledge base that highlights areas that need to be improved?
That is an excellent question. So I don't think there is a way to create one knowledge base with all the open questions. I think that would be rather difficult. But what we need to encourage is the exchange between industry and research. So I would say this is really domain specific and should be tackled at conferences as well. Something like what needs solving. So where people could come and ask questions, say, okay, we have like this 10-minute slot, 5-minute slot where they pose a problem and say, go, we have this problem. I think it would be very interesting, and I think it would help accelerate many solutions. Other question to this is whether the people would be willing to do so. I'm not so sure, but it would be interesting to try it. Another thing which I have also discussed in my paper, which I think would be good, is to enforce peer reviews by applied research institutions. What I mean by that is there are a lot of institutions which kind of connect research areas, universities, and the industry. Fraunhofer, which I'm working for, is one of such institutions. Goal of that is to kind of decipher research and really make it bulletproof and working in the industry and robust enough. If those people would be made part of peer review, they would be able to propose new applications, or to reading on a paper, they would be able to propose other applications other than the work itself, because those are the people who know what has been needed, what's needed, but they also are capable of understanding the research paper. So it would be kind of a very interesting peer review feedback. That doesn't say, your research, I don't like it. It says, oh, okay, cool research. These are the things that we think should be changed, but this is something that can be considered and might be even do something like journals or conferences on proceedings, something like comment section, applicable fields. So something like that.
Okay, I want to ask you a last question. So there are a couple of more, and if there's time in the end, I will probably post them. And I also want to value the vibrant discussion that already among the presenters was there on YouTube. So maybe you can just step in if you want to contribute into the discussion. So just wave your hand and just fine. There was a question on the publishing of code, which I also found interesting, because this is something like our publication policy. So typically we do not publish code, but does it have an effect, or is it like Ulrich said, is it in your experience so far met with agreement or resistance with your partners?
So I would say it's definitely matter on the attitude of the research group, whether they want to publish code or not. People are in general, if you ask anyone, should the code be published, they will say yes, because every one of us has benefited from the code that was available somewhere, because you can look at it, you can edit it, you can try something real quick. However, when it comes to a single person publishing their code, I think there is a problem that oftentimes I've heard that they're embarrassed to publish their code because they don't like the way it looks. So this is some kind of a problem, but it, I mean, it's true. We write code for ourselves and we don't expect anyone to look at it. And then if we do it like that, we will be embarrassed saying like, we are computer scientists after all, when we do know that good code has a certain structure and we do know when our code doesn't. But it is a question of agreement. And I think the groups should be more open to it.
Some call it write-only code, right?
Oh, that's a nice name.
Okay. So thanks, Petra. And Thomas, you joined the groups. Do you have a specific question you want to pose? Let's see. Maybe later on. So Renata, I liked your workflow, which is like, I mean, I work together with humanities scholars, and it fits perfectly. It's, instead of the clinical assessment, everything else is there. There were some questions for you. So what would you say? Would you say that incorporating uncertainty into the visualization was the key development in this scenario? And do you think this applies to other cases in medicine as well?
Yeah, so uncertainty in general is a dear topic to me. And I believe that in general, the incorporation of uncertainty within visualizations, especially for a medical purpose, is really critical. And it has not been tackled as much as it should have in the past. And within this project, uncertainty, especially in the form of variability within a cohort, is the core of the applications. And as cohort and population studies are becoming increasingly popular, I think that they will become of interest to many more medical visualization applications. So linking it to a previous session, from the point of clinical practice, I have very often encountered a very strong resistance from domain experts. And they often say, yeah, it just burdens my decision-making processes. I just want to, in the best case, see a go, no go. But they don't want any fancy encodings, any additional stuff there. But within this project, which is more related to a clinical research topic, uncertainty, variability, visualization was actually requested by the domain experts themselves. So in general, I can just say that I'm always interested in seeing how uncertainty visualization is accepted by different kinds of domain experts, especially within medicine. And I think that it's a quite tough topic within the whole radiotherapy workflow. So I hope that there will be much more stuff in the future about it.
Okay. I was wondering, so in case you generate a very, very beneficial method that obviously works in the clinical work, so how long would it take to establish a new method in the clinical routines. So I guess this is a long path from just developing to really making benefit on the other end, right?
Yeah. So actually, this is a great question, and in our case, this whole thing started with other projects, something like 8 years now. Within this variability project, we started working, I think, 4.5 to 5 years ago. And as you saw, it was a continuous process of we developed something, we evaluate it, then there was like a clinical study going again back, and so on and so forth. So I don't know for how long this will last, but so far, yeah, it has taken quite significant time. But it was possible even to reach it to the clinical study point because it is done with data that have been acquired already in the past. So those are patients that were already some years back, and there are even assessments of how their health went after the whole radiotherapy process. So if it would be actually needed to be put into clinical practice, this would require other things like certifications and FDA approvals and so on and so forth. So these can last up to many years, obviously.
Okay, okay, that's a pity somehow that it takes so long. Okay, but thanks for the first answer. So I will head to the next one, and yeah, depending on the time, I will come back to you. So let's ask Martin. So as I already mentioned, I saw that opening Wordle and trying out something worked at some point of time, not anymore. So I was wondering. I mean, you choose to go back and go back to the Java source and not choosing to somehow find a solution to use JavaScript. So I guess there are different approaches. I was wondering, can you tell us something about your users? So are they capable of running a Java application, or are there also users which you lose by that design decision?
Actually, before I answer that question, let me really briefly come back to something Petra said earlier, which I just really liked. You suggested that we should have like sort of open problem sessions. And I wanted to share with you that we had something like that during a workshop at the Institute for Computational and Experimental Research in Mathematics last year. During all our workshops, we had just a board standing in a corner. Everyone could write problems on it, put their names behind. And so people who thought, oh, I might be able to help with this one, could find those people throughout the workshop, and then they could start collaboration. I think that was just fantastic, and I would love if all the conferences would just have a board like that. So maybe we can start. We have Discord, right? So
this is really cool. This is really cool. Maybe we can do something like that goes like at the point when the papers are submitted, someone can also submit a problem. So we have kind of a board of submitted questions, and by the time the conference comes, we pick the most interesting one and we actually discuss them. So you can have on a conference kind of a joint brainstorming on how to solve different things. It would be also quite good for networking.
All right. So coming back to your question, Stefan. Yes, indeed. So Java is, I'd say like a couple of years ago, it wasn't that problematic, but and we still used it a lot in Berlin. For teaching purposes, actually. We have a visualization seminar there where all the students install the software and then use it to do their own visualization experiments. However, that becomes more and more difficult. I don't know whether you tried lately to install Java on a Mac and then get all the different packages running. That's getting harder and harder, and maybe Ulrich can say a little bit more about how Java is widespread and still supported. Well, we basically went that way of not going to JavaScript because we didn't want to lose the sort of high-level algorithms. And that's we felt that if we went to JavaScript and implemented a simple web viewer framework, then these web viewers wouldn't necessarily be able to support these like deeper, more computationally intensive algorithms. So yeah, I think that's really something I try to make point out in my talk, that we all come to this point where we need to see, okay, does my software actually still satisfy the goals I set out for it? Yeah, it becomes really critical if we find that it doesn't, right?
Okay, there was another question by Petra. She was posting it online. My son is just yelling at the door, so maybe you hear it. So typical problems of a virtual conference. So and he doesn't stop. Okay, so Petra asked if you think that browser-based...
If you want, Stefan, I can ask the question again.
Yeah, that would...
The question was rather, so what do you think about browser-based solutions? And I mean, computationally, they are quite difficult. I mean, wonderful thing about JavaScript is it's easy. It doesn't pose too many restrictions. A horrible thing about JavaScript is it has no threads. You cannot make it multi-threaded. You have possibility of using web workers, but I've tried going into that once and I stopped. Exactly. So if you do something browser-based, it will be available to basically anyone. Okay, there are some differences between the different browsers, but the problem is, can you really make something powerful with it, and how to tackle that problem?
I think that's really interesting because it comes back to what do you want to do with your software, right? So going back to the very origins of the Java View framework, it was meant to be an online visualization framework for easy, quick online experiments you could do, play around with a bit of mathematics, gain some insight. So it didn't need to be very powerful. And it only over the time developed into this framework where the applets were taken away and there wasn't like such a widespread support for JavaScript, no WebGL yet. So it developed into this high-level framework, and now stepping back, going to JavaScript, reducing everything to this lower level, let's play around a bit approach seems to be a pretty bold developing choice that definitely could be made, right? There are other frameworks though that do this pretty successfully. I think in my paper I listed the Cindy.js framework, which is basically the JavaScript wrapper for Cinderella. Then GeoGebra is running online pretty successfully. And then the question is again, like, do you really want to throw out another framework there? Or isn't the visualization community, also the online visualization community, not fragmented enough yet? But yeah, I think there's people do quite some interesting stuff with JavaScript. But if you really want to do a serious visualization with it and geometry processing, yeah, I don't see that happening completely online.
Okay, thanks for continuing the discussion. I needed to solve a problem. Yeah, thank you. Maybe we can head to Ulrich, because Ulrich shows the different approach, because you basically redeveloped something and did not decide to take on the developments of the old deprecated source. So, and I guess Martin asked the question, so why did you choose that path?
Well, we actually tried taking on the old code and trying to modernize it, but after a while got actually pretty frustrated and thought, okay, there's an amazing amount of stuff here that we would actually like to get rid of. And we would like to have a more flexible infrastructure that could allow us, for example, replacing the rendering code in the future. While the old viewers were very strongly tied to OpenGL versions, and usually they're pretty old OpenGL versions, so like OpenGL 1.2 or maybe 1.5. And that was so deep in the code. It was also some, back then, probably good decisions. But now when you look at that, you think, why did you do that? And so this was, I guess, the main reason why we started this new project. And another thing is I actually really don't like Java. So we had to look around the JVM ecosystem, and I think the JVM is actually awesome, but Java is a pretty horrible language. And back when we started the new project, there was Kotlin coming around. There was also Clojure and some newer kits like Ceylon and others. And we in the end decided to use Kotlin because it was commercially supported by JetBrains. And this was originally met with a lot of skepticism, like, okay, this language is going to die. And a year later, I could tell people, guys, Google adopted this language for Android. I won. So this could not have been foreseen, but I guess it worked so far.
I mean, the previous 3D viewer got deprecated in a way because the maintenance decreased and stopped finally. So, what are your measures to make sure that your solution is maintained in 20 years? So, is there anything? how do you can ensure that your solution?
That's of course very, very difficult to predict, right? And also in terms of funding, in terms of what jobs people get. I think everybody here is familiar with the issues people face in scientific software development. However, we try to make things a bit more easy by trying to document the code itself well. I have to admit we still have a bit of lack on documentation on the book kind of side or tutorial kind of side. But we try to also implement a lot of tests and so on. So when somebody else takes over the code, can easily, maybe not from one day to the next, but maybe over a period of a month, also get deep into the code base, understand what's going on, and take it over and continue developing it. Mm-hmm. And as I showed on one slide in the talk, we have automated a lot of these steps also with like the stuff that runs on the continuous integration system, sometimes in containers, sometimes not, where you get immediate feedback on whether some test fails, or even visual feedback whether something is now suddenly rendered different than it was before. So I think this is maybe not a silver bullet, but it at least helps the process. So for the older viewers, we did not have something like that in place, probably also because I think in 2010 not a lot of people actually thought about continuous integration and continuous deployment. So I hope that this will at least provide a bit of longer term sustainability help, so to speak. And I mean, we also try to get different institutes involved, so there's also kind of a more backing in funding and manpower. So let's see how that goes.
Okay, a remark from Johanna Schmidt on Discord. She says, I have the feeling that the pros, which are mainly keeping track of your workflow and sharing the work, are stronger than the cons. Which is the strict linear layout. I agree.
I think this was from a comment I made on the Discord earlier.
Oh, this is but anyway, so that was I just thought
I would like to make a small comment on what Martin said with the deployability of Java and so on. So with Fiji, we are in the kind of convenient place where Fiji actually ships with a JDK and a JRE. So people don't need to download that separately, which is pretty nice. And Oracle recently kind of changed the licensing stuff for the JDK they produce, but there is still... Sorry, should I stop?
Yeah, we are running out of time.
Oh, sorry. Maybe we can continue on Discord or something.
Yeah, I thank you for the vibrant discussion, and you can continue discussing on the Discord. So thanks all for your contribution, and see you later.
Thank you, guys.
Bye. And this concludes the session.
Thank you.
Thank you.
Thanks, bye.